Good evening, everyone. So in this lecture, we'll be starting with the magnetic flux today, right? Then later in this lecture, we'll be discussing about the electromagnetic inductions and laws of the electromagnetic inductions. That those are the Faraday's law, right? There are two laws of Faraday, right, with respect to the electromagnetic inductions. And then we'll also study about the Lenz's law as well, right? So let's start with the magnetic flux, right? In the previous few lectures, we discussed about the magnetic field lines, right? Discussed about the properties of the magnetic field lines as well, right? We said important properties of the magnetic field lines are that these electric magnetic field lines are actually they form a closed loop, right? They form a closed loop. It means that we concluded that the magnetic monopoles actually do not exist, right? They always form the closed loops, right? And the direction of the magnetic field lines are from the north pole of a magnet to the south pole, right? And we also discussed a very important property with respect to field lines was that the two magnetic field lines actually cannot intersect each other because we know that uh, the tangent to the magnetic field line at any point on the magnetic field line gives the direction of the net magnetic field at that point, right? And if the two magnetic fields actually intersect each other, it means that there will be two tangents. There will be two different tangents at the same point, right? Giving rise to the two different direction for the magnetic field, right? Giving rise to the two different direction for the net magnetic field. It means that the magnetic field at that point is going to have uh, two directions, which is not possible, right? So that's the reason that magnetic field lines will not form a will not actually intersect each other at any point, right? That will give rise to the two different directions of the magnetic field. So this is the reason we do not, we say that magnetic field lines do not intersect, right? And one another important was that magnetic monopoles do not exist. Whenever we cut a magnet, it always exists as a dipole, right? There are two poles, one is the north pole and another is the south pole. In the same way, we discussed about the current loop as the magnetic dipole. Current loop also behaves as a magnetic dipole, right? For the anti-clockwise current, it behaves, the front face behaves like a north pole and the back face behaves like a south pole. And in the same way, for the clockwise direction, the front face of the coil will behave as the south pole and the back side will behave as the north pole of a magnet, right? But today we are going to do some discussions with respect to one of the important discussions with respect to the magnetic field lines. So magnetic flux actually we have studied in electrostatics as well, where we discussed the concept of electric flux, right? But now we'll be discussing about the magnetic flux, right? So in the magnetic flux, what we study is that let's suppose that we have this arbitrary shape of area, right? Arbitrary shape of area, right? This is the area, right? This is the area, and there is some magnetic field in this area, right? There are some magnetic field lines in this area, and these magnetic field lines are actually a non-uniform magnetic field lines. You can say that these magnetic field lines are not actually parallel to each other, right? So these are the magnetic field lines, right? Magnetic field lines. Now let's suppose that I am choosing an area element here. Let's suppose this is the area element here, right? This is the area element here. I am choosing this area element here as ds, and the direction of this area element is along this direction. I call this direction as eta cap, or we can write this ds as area vector. That's the ds vector, right? And let's suppose let's suppose at this point, the direction of the magnetic field is, let's suppose it's along this direction, right? It's along this direction, right? This is the direction of the net magnetic field at this point, right? So this is the direction of the magnetic field P. Or we can say that the angle between the area vector and the magnetic field vector is theta, right? Then the flux through this elemental area, right? Flux through this elemental area will be given by d phi. It will be a flux d phi that will be given as the dot product of this magnetic field vector with respect to this ds vector, right? Magnetic field vector with respect to this ds vector, or we can write this b vector ds vector as magnitude ds multiplied by the unit vector associated with this area vector, that's eta cap, right? So this is how we can represent a flux through this area element ds, right? This is the flux through this area element ds. And if you want to calculate the flux through the whole area, right? Through the whole area, right? Then what we have to do is that we have to integrate it both sides to calculate the flux through the whole area, right? So integral d phi will be phi, right? It will be integral of p vector dot ds vector, right? So this is what we call as magnetic flux, right? This is nothing, this is the magnetic flux. So this is what we call as the magnetic flux through any area, right? So it actually gives ideas about the intensity of the magnetic field or the magnetic field lines, or it's a measure of the magnetic field lines actually, measure of a magnetic field lines or the density of the field lines which actually crosses through an area, right? So that's how we that's what the significance of magnetic flux is, right? This is the significance of the magnetic flux, correct? So let's suppose that if p is a uniform magnetic field, right? P is a uniform magnetic field. If p is uniform magnetic field, uniform magnetic field, p is a uniform magnetic field, correct? If p is a uniform magnetic field, that then in that case we can just take b will be a constant vector, right? It means that uniform magnetic field means that magnetic field vector will be a constant vector, right? It will be a constant, right? Magnetic field vector will be a constant vector. It means that we can take this magnetic field vector out of this integral, right? If we take this magnetic field vector out of this integral, we'll be left with p vector dot with integral of this ds vector, right? Integral of this ds vector, right? Integral of this ds vector, and integral of this ds vector will give us the area vector a vector, right? We can write it as b dot a. We can write it as b dot a, right? It will give us the b dot a vector, or we can write this magnetic flux due to uniform magnetic field, right? Due to constant magnetic field, that will be dot product with the area vector and the magnetic field vector, right? And we know that this area vector is actually a vector which is associated with the area, right? It's a vector associated with the area, and this area vector tells us about or gives us the information about how much flux actually is going to flow through a given area, right? So that's the importance of this area vector, right? This area vector is perpendicular to the area and away from it, right? And orientation of this area vector with respect to the magnetic field vector gives us the idea about how much flux or the how much magnetic field lines are, or we can say the density of magnetic field lines passing through the given area, right? And if the angle between this b vector and area vector is theta, we can write this b dot a as p a cos of theta, right? P a cos of theta, or we can say that it's the projection of the magnetic field along the given area vector, right? So we can say that it's a projection of magnetic field lines along a given area vector, correct? So this is how we define the magnetic flux through a given area, right? We can see here these are the uniform magnetic field, right? These are the uniform magnetic field lines, right? Uniform magnetic field lines are always represented by parallel lines with equal spacing between them, with equal spacing between the lines, right? There are straight lines and parallel having the equal spacing between them. These are the uniform magnetic field lines, and in the same way we represent the uniform electric field lines as well, right? And this is the area vector. This is the area vector, right? And area vector is perpendicular to the given area and away from it, right? This is a vector associated with the given area, right? And its orientation with respect to the magnetic field is very important to calculate the amount of flux passing through the given area, right? If theta is the orientation, or we can say theta is the angle between the area vector and the magnetic field vector, then the flux is b cos b dot a or b cos theta, right? You can see this example here. Now here, this is the area, right? This is the circular plate here, right? This is the circular plate here. And this is the circular plate, and this is the uniform magnetic field, right? This is the magnetic field lines, right? Direction of magnetic field, and this is the direction of area vector, right? This is the direction of area vector, or you can say the angle between the area vector and the magnetic field vector is actually 0 degree. It means if angle between area vector and magnetic field vector is 0 degree, or we can say that in that case the value of phi will be nothing. It will be ba cos 0. That's cos 0 is 1. It will be ba. So ba, it means that when the angle between the magnetic field and the area vector is 0 degree, then the maximum flux will be passing through it, or we can say the flux associated with that area will be maximum, right? It means the density, it means the maximum number of field lines that could pass between a given area or through the given area is actually BA. It's only possible when the angle between the area vector and magnetic field vector is either 0 degree or 180 degrees. So it's entering flux, right? Flux passing through this area. So it's a BA flux, right? Plus flux is here is equal to B into A, right? In the same way, let's suppose that if the magnetic field is directed along this direction, right? This is directed along the X direction, right? And this is the direction of the area vector, right? And this is the direction of the area vector, correct? So if this is the direction of the area vector, you can see that area vector and the magnetic field lines are actually aligned at an angle of 180 degree, 90 degree with each other, right? 90 degree with each other. Right? If 90 degree is the angle between the area vector and the magnetic field vector, it means that all the field lines will be passing through this plane like this, parallel to this plane, right? But no field line, no magnetic field will be entering to this area, right? No field line actually cross through this area. It means if no field line is going to cross through this area, all these field lines will actually pass parallel to the plane of this disk, right? Parallel to the plane of this area or parallel to the plane of this disk, or we can say that the flux through this plane will be actually zero, right? There will be no flux or there will be no field line passing through this plane, right? We can see it like this also, be a cos of theta, right? And be a cos of 90 degree is nothing, cos 90 is zero, so there will be no flux or no field line, magnetic field line passing through this area, right? In the same way, let's suppose if this is the area, right? If this is the circular area, right? If this is the circular area, and this is the area vector, right? This is the area vector. This is the area vector, and this is the magnetic field lines passing through it. And we can see here that the angle between the area vector and the magnetic field lines are actually 180 degree, or we can say the flux here is nothing. That's equal to BA cos 180, or we can say it is minus BA, right? It's a negative flux, right? Negative flux. So it means the flux is negative here, right? Yeah. But the magnitude of the flux is once again BA. So the maximum flux is possible only when the two orientation of A vector and B vector is either 0 or 180 degree with respect to each other, right? Now let's try to solve this question. A loop of area 0.06 meter square is placed in a magnetic field of 1.2 Tesla with its plane inclined 30 degree to the field direction. Find the flux with the plane. Now inclination of the plane here is given that it's inclined at an angle of 30 degree to the field direction. It means that this area vector will be actually inclined at an angle of 30 degree. This area vector will be inclined at an angle of 30 degree with the magnetic field vector. So this is the magnetic field vector here, right? B. And this is the inclination that's equal to 30 degree. Or we can say the flux will be nothing. It will be BA cos of 30 degree, right? Cos of 30 degree. And cos 30 is root 3 over 2. You can write it as root 3 over 2 multiplied with B, that's 1.2 into area of this loop, right? That's given at 0.06 meter square and multiplied by 0.06. So this will be the flux, right? This will be the flux, and the SI unit of the flux is nothing, is Tesla meter square, right? It's Tesla meter square is the SI unit of this flux, right? So this will be the amount of flux passing through this area, inclination having 30 degree with respect to the field, right? Now let's try to solve this problem as well. A loop of wire is placed in a magnetic field, right? We have been given a loop of wire which is placed in a magnetic field, and the magnetic field is directed along a direction of 0.3 j cap, right? 0.3 Tesla j cap, right? So magnetic field here in this question is given as the magnitude of the magnetic field. Magnitude of the magnetic field in this question is given as P vector is given as 0.3 Tesla, and it's directed along j cap. It means it's directed along the positive y direction. If it is directed along a positive y direction, and the area vector is given as 2i cap 5j cap plus 3k cap, right? Now the magnitude of this area vector will give us the magnitude of that area to which this area vector is associated, right? The magnitude of this area vector will actually give us the area of that area, right, or that loop to which this area is actually associated, right? So this is the area vector, right? Now the flux passing through through it will be nothing. It will be B vector dot with A vector, right? And it means the only magnetic field which will be passing through will be the magnetic field line which is along the direction of this B vector. That's J cap component, right? Two I cap component will not pass through it, and K cap component will also not pass through this area. The only component of this magnetic field which will pass through it will be the J cap component, right? So it means that the phi here will be 5 multiplied by 0.3, that will be equal to 1.5 Tesla meter square. That will be the flux associated with this will be the flux associated with this area vector having the magnetic field 0.3 Tesla along J cap direction, right? Now let's discuss these questions here, right? You can see here the question says that at a given place, right? At a given plane, horizontal and vertical component of Earth's magnetic field PH and PV. There are two components of the Earth's magnetic field. One is the horizontal component, we represented by BH. Another is the vertical component, which represented by BV. Right? They are directed along Y direction and X direction, respectively, as shown in figure. What is the total flux of Earth's magnetic field associated with an area S if the S is an XY plane, YZ plane, ZX plane, right? So these are the three planes here, right? These are the three planes here, right? For part A, this is the loop placed in XY plane, right? And this is the direction of the magnetic field, vertical magnetic field that's along a downward direction, and this is the horizontal magnetic field. It's along plus x-axis, right? And this is the area loop, right? And you can see that if this is this is the loop, how it is actually directed. You can see this will be the area vector associated with this loop, right? This is the area vector associated with this loop, and you can see the direction of this area vector is along, or we can say it's parallel to this z line. It's parallel to this z line, right? It's parallel to this z line, or we can say this s vector is nothing. Its area is s, and it is directed along k cap direction, right? We can write it as s times k cap, right? K cap is the direction for this area loop, right? And this magnetic field due to Earth is nothing. It's directed along x direction and y direction. We can write it as ph I cap, or we can write it as plus pv bv. It's along negative y direction. We can write it as pv minus pv j cap, right? Minus pv j cap. So this is the magnetic field due to the Earth, right? And the flux because of Earth's magnetic field through this loop, when it's placed in XY plane, it will be given by, so phi here will be actually equal to B vector dot with this SK cap vector, right? SK cap. So it will be actually PH I cap minus PV J cap, right? Minus PV J cap dot with SK cap, right? So it means that the dot product here will be 0, right? Phi here will be equal to 0, right? If phi is 0, it means that actually no magnetic field line will be passing through this area, which is placed in this XY plane because of the Earth's magnetic field, or the Earth's flux due to Earth's magnetic field through this loop, which is placed in XY plane, will be equal to 0, right? Now let's talk about the flux about this loop, which is actually placed in YZ plane, right? Which is actually placed in the YZ plane, right? Through this loop, right? You can see that here, this S vector is along the direction of this X direction, right? Or we can say that this S vector can be written as magnitude of S, and just directed along plus X direction. We can write it as SI cap, right? SI cap. So the flux through it will be phi will be given as B dot A, right? B dot A, P dot A, or if this is B dot A, we can write it B dot A, that's PHI cap, right? PHI cap minus PV J cap dotted with this SI cap vector, right? SI cap. So it will be actually PH times S. This will be the flux through this loop because of this magnetic field due to Earth, right? And let's similarly for this third case, you can see that here in the third case, the S vector is directed along the plus y direction. So we can write it as S vector as S is the magnitude of this loop, right? And it's directed along j cap. We can write the flux through this as phi times phi is equal to bhi cap, right? Bhi cap minus pv j cap times dotted with sj cap, right? So the flux here will be actually minus pv s, right? So this will be the flux through this loop, right? So this is how we can calculate the flux through different loops, through different situations, right? In different situations, right? But we have to make sure that we calculate the proper direction of S vector with respect to the magnetic field vector, right? Now let's move on to the important topic or the important concept, right? That was which is with respect to this magnetic field, right? Which is with respect to this magnetic flux, right? These are the electromagnetic inductions where we actually get the induced electric field and induced EMF, right? That's the Faraday's experiment, right? So Faraday Faraday did an experiment, right? Faraday had an idea that when when current can actually current can actually establish a magnetic field around around the conductor, right? When a current flows through the conductor, the magnetic field gets established around a conductor, right? When a current flows through a conductor, magnetic field gets established around a conductor. In the same way, in the same way, he actually predicted that using the concept or because of the concept of the symmetry, that he predicted that if it is possible to have a magnetic field because of the current flowing through it, right? Because of the current flowing through the conductor, right? Because of the current flowing through the conductor, right? So can we have the current flowing through the conductor because of the magnetic field, right? So for that he established or he did some experiments to calculate the current flowing through the conductor, right? To calculate the current flowing through the conductor, he did some experiments. The experiment was that uh, in this diagram, you can see there is a circuit, right? And in this circuit, we have this coil, right? And to this coil, we have connected a meter, right? And we have this bar magnet, right? We have this bar magnet. What he did in this experiment is, first of all, he placed a bar magnet here, and we know that the magnetic field lines because of this bar magnet are directed like this. These are the magnetic field lines. They originate from the north pole, right? And they terminate on the south pole. So these are the magnetic field lines because of this bar magnet, right? Because of this bar magnet. These are the magnetic field lines. So what he did is that when he placed a bar magnet at rest near this circuit, right? Near this circuit, he found that there was actually no deflection shown by this galvanometer in this circuit, and he concluded that when a magnet is placed near the conductor, near the circuit, right, near the circuit at rest, then he observed that there is no deflection in the galvanometer, or he observed that no current is actually established in the circuit, right? No current is actually established in the circuit. So this was the first point, that when the magnet is held stationary anywhere near or inside the coil, right, with velocity equal to zero, no deflection is observed by the galvanometer, or we can say galvanometer did not show any deflection, right? In the second way, what he did is that when the north pole of a strong bar magnet, he actually used a very strong bar magnet, means the bar magnet of high intense magnetic field, right? He moved this bar magnet towards the coil, right? Towards the coil with some speed, right? You can see here, towards the coil with some speed, right? Towards the coil with some speed, right? And he observed that there is some deflection shown by the galvanometer, and this deflection was towards the right, right? It was towards the right. It was towards the right of the zero mark, right? So he actually observed that whenever a magnet placed near this circuit is actually moved towards this circuit or towards this conductor, then some deflection is observed with the help of this galvanometer, or we can say the current was measured by the galvanometer, right? Then what he did is that when the north pole of a bar magnet is moved away from the coil, what he did in the first case, he moved the north pole towards the coil. Now he is moving the same north pole away from the coil, right? It's moving the same north pole away from the coil. Now, in this case also the deflection was shown by the galvanometer, but now in this time this deflection was not towards the right. Now this time the deflection was towards the left of the zero mark or left of the zero reading of this galvanometer, right? Right. So in the same manner, all these experiments were actually repeated with the south pole as well. This is the south pole, right? Now the south pole was moved towards this meter, right? Towards this circuit, and now this time the deflection was observed towards the left, and similarly, in this case, when south pole is moved away from the conductor, away from the circuit, the deflection was observed towards the right. So these were the observation. Actually, what he observed is that whenever a magnet is moved, the current is actually established in a circuit, right? He did not he did not give any explanation till now what was the reason behind it, right? But this was just the experiment. The experiment was that when the bar magnet was placed near the circuit at rest, then at that time there was no deflection shown by the galvanometer, right? But when this bar magnet was moved towards the circuit, there was a deflection, right? And when this bar magnet was moved away from this uh, circuit, there was also a deflection, but the deflection was in the opposite direction, right? And same goes with the south pole and north pole. But there was one more observation, one more important observation, right? What he did that if he very quickly moved this bar magnet towards the circuit, the deflection he observed was greater, right? It means that if the bar magnet is moved faster towards the coil or faster away from the coil, the deflection actually measured is greater and greater, right? So as quickly we move this bar magnet towards the circuit or away from the circuit, deflection or the measurement of this galvanometer increases, right? So this was the uh, very important observation. It means that it depends upon the speed of this bar magnet also, how actually the how larger the deflection will be. It also depends upon the speed of this bar magnet as well, right? So with respect to all these observations, what Faraday did, he did some conclusions, right? He did some conclusions. He concluded all these observations, all these experimental observation in the form of certain laws. That's the first law of Faraday and the second law of Faraday, right? So the first law of Faraday says that why does actually the current flow through the circuit, or we can say how does actually the EMF gets induced in the circuit, right? He said that it's actually the magnetic flux. It's not the magnetic field only, because the magnetic field was also present there when the bar magnet was placed near the circuit. Magnetic field was present there, but there was no induced EMF or no induced current in the circuit. So what he concluded that it's not the magnetic field, it's actually the magnetic flux linked with the closed circuit that induces the EMF in the circuit, right? And this induced EMF lasts as soon as the magnetic flux continues to change, right? Once the magnetic flux ceases to change, there is no induced EMF. The induced EMF stops, right? So this was the first law that Faraday gives that it's the magnetic flux, or we can say it's the change in magnetic flux. It's the change in magnetic flux which actually induces the EMF in the circuit. It's not the magnetic field, right? It's not the magnetic field which induces the EMF in the circuit. It's the change in magnetic flux which induces the EMF in the circuit. And this induced EMF lasts as soon as the change in magnetic flux continues, right? As soon as the change in magnetic flux continues in the circuit. So this was the first law of Faraday. And the second law of Faraday was that the magnitude or the amount of magnetic flux, amount of electromagnetic induction, right? The magnitude of this EMF induced in a closed circuit actually depends upon the rate of change of magnetic flux with respect to the time in the circuit, right? It means that if the rate at which the flux changes through the circuit increases, the EMF induced will increase. If the rate through which the flux actually changes in the circuit, then the EMF induced is less, right? So this was the important observation. So we can just write this mathematically that the EMF induced is actually directly proportional to the d phi over dt, right? D phi over dt, right? So this was the law given by the Faraday. So this is nothing. This is the Faraday's second law, right? Faraday's second law. Faraday's second law. So Faraday's second law says that the EMF amount of EMF induced in a circuit is actually proportional to the rate of change of flux through the circuit, right? Rate of change of flux through the circuit, right? And flux, we can write it as, flux is nothing, it's P dot A, right? P dot A, that's equal to PA cos of theta, right? PA cos of theta. Right. Now the question is that how we can change the flux, how the flux can change. The flux can change through different ways, right? The flux can be changed if we change the magnetic field also, right? If magnetic field changed, then the flux can be changed. But the area of a section is actually always a constant, right? We cannot actually increase and decrease. It's not possible for us to uh, increase and decrease area of a conductor simultaneously, right? So the only thing that we can actually change is the orientation of this magnetic field with respect to the area vector, right? With respect to the area vector, right? So if we actually change the magnetic field, then the flux linked to the conductor change, then the EMF is induced, right? If we change the orientation, or we can say the angle between the area vector and the magnetic field vector, in that case also the EMF will be induced in the circuit, right? EMF will also be induced in the circuit. So there are two ways, actually, basically two ways we can change, two important ways we can actually change the flux. One important way is that we change the magnetic field, or we can say that magnetic field is actually a magnetic field P is actually a time dependent, right? It's actually a time dependent. It's actually a time dependent. If the magnetic field is a time dependent field, right? Time dependent magnetic field, then in that case flux through the linked surface will be actually will actually change, and the EMF will be induced. And we can also change the orientation. How we can actually change the orientation? You can see that. Let's suppose this is the area loop, right? This is the area loop, and this is the direction of the magnetic field. This is the direction of the magnetic field, right? This is the direction of the magnetic field. If we rotate this area loop continuously, right? If we rotate this area loop with the angular velocity of omega, what is going to happen? At different times, the orientation of this area vector will be different, right? Orientation of this area vector will be different, right? So it will be differently oriented with respect to this magnetic field vector. If the orientation upon rotating this loop, the orientation of the magnetic field vector with respect to the area vector will change, and the flux through the loop will change. If the flux through the loop will change, then the EMF will be induced, right? We'll be studying that. Will study this how actually the AC generators work in the same way. The AC generators also work in the same way, that when we rotate the loop, current carrying loop or the conductor, then the orientation of field lines with respect to the area vector change, then the flux change and the EMF is induced, right? So this is how we can change the magnetic flux by changing the orientation, right? And the magnetic field we can change. If we have a magnetic field as a function of time, then flux will also be induced, right? Now the question is that how actually the induced EMF, actually we just mentioned, second law just mentions that it's proportional to the rate of change of uh, flux with respect to time. So what about this proportionality constant, right? It's a proportionality here, but is there a constant, right, to replace this proportionality, right? So actually Faraday did not had any idea. So what is the orientation? What is the sense of this induced current, right? So this was actually explained later on by Lenz, right? Lenz through different experiments said that actually uh, that's right, that EMF is actually directly proportional to the d phi upon dt. That's nothing. That's the Faraday's law, right? That's the Faraday's law. That's Faraday's law, right? But he replaced this proportionality with a negative sign. He said that it's actually minus d phi over dt, right? It's actually minus d phi over dt, right? It's actually minus d phi over dt. He replaced this proportionality with minus one, right? Minus one. and he explained that why actually the minus sign is there, right? Why actually the minus sign is there. So he explained that this negative sign actually gives us the orientation or the sense of the current induced, right? And this says he Lenz law said that Lenz said that whenever an EMF is induced in a circuit, then EMF always opposes the cause of that EMF induced, right? The EMF induced always opposes the cause of induced EMF, right? It means that you can see here this is a bar magnet here, right? This is a bar magnet, and the north pole is towards the coil, right? North pole is towards the coil. If the north pole is towards the coil of this north pole is towards the coil of this loop, right? Then these are the magnetic field lines, right, associated with this loop because of this north pole, right? Because of this north pole. Or we can say that the magnetic flux is associated with this current loop, right? Magnetic flux is associated with this current loop, correct? So this is the magnetic flux associated with this current loop. Now, as the bar magnet moves towards the coil, the intensity of this magnetic field lines increases, or we can say the flux through this loop actually increases. If the flux through this loop increases, it means that now the flux change, EMF will be induced. Now this EMF will be induced in such a way that the induced EMF will oppose the cause of this current, right? And the cause of this current is actually the increase in the magnetic flux, the increase in the magnetic flux. Now, the induced EMF will be in such a way so that it will try to reduce the amount of the magnetic flux, right? It will try to reduce the amount of magnetic flux, right? So the sense will be in such a way so that the magnetic flux through this conductor actually it tries to decrease the magnetic flux through this conductor because bar magnet tries to increase the flux. Now this induced EMF will try to decrease the magnetic flux. So in order to decrease the magnetic flux, the current must flow anti-clockwise, because if we calculate the direction of the magnetic field because of this induced EMF or induced current, it will be actually along this direction. It will be along this direction. So this will be the direction of the magnetic field lines because of the induced EMF, and these are the direction of the magnetic field lines because of the bar magnet. So, or we can say that the magnetic field lines of the bar magnet here in case first actually opposes the magnetic field due to the induced EMF, right? In the same way, you can see here, in the same way, in the case second, now the bar magnet is moving away from this coil, right? But still the flux field lines are linked like this, right? These are the linked field lines because of this bar magnet with the loop, right? As this bar magnet moves away from this loop, the flux through this loop actually changes. Induced EMF will be there, right? Now decrease in flux induces the EMF because the magnetic field intensity decreases as soon as the magnet moves away from this coil. Now there is an induced EMF because of the decrease in the magnetic flux, right? Decrease in the magnetic flux. Now induced EMF will try to increase this magnetic flux because we know that EMF always opposes the cause. Decrease in EMF, decrease in magnetic field lines through the loop is the cause of this induced EMF. And this induced EMF will try to increase these magnetic field lines. It will try to increase the magnetic flux through this loop, right? So current will be in current in this loop will be in such a direction or in such a sense so that the magnetic flux through this loop increases, right? So this is the magnetic field line. So in order to increase the magnetic flux through this loop, the current will be in a clockwise direction, and because of that clockwise current, the magnetic field lines will be along the direction of these magnetic field lines, right? So that the flux increases, right? So that the flux increases. Or in nutshell, we can say that Lenz law states that the uh, change always opposes the cause, right? Change always opposes the cause. What's the change here? Induced EMF always opposes the cause, right? Or we can say induced EMF always opposes the change, right? Whatever change we bring in the form of magnetic flux to this loop, it will the current through it will be induced in a such a way so that it will oppose the change, right? It will oppose the change. Otherwise, if it's not so, then it will be like a perpetual motion machine. It means we are getting the energy out of nothing. So it means that Lenz's law actually signifies the law of conservation of energy. Law of conservation of energy. Law of conservation of energy is the significance of Lenz's law. Law of conservation of energy. This negative sign here actually implies the opposition, right? Opposition to the change, right? It actually signifies law of conservation of energy, right? Law of conservation of energy. So this is the Lenz law, right? This is the Lenz law. Now let's try to solve few questions with respect to Lenz law. Then in the next lecture, we'll be discussing about the self-inductance and the mutual inductance as well, right? You can see here the question is the radius of a coil decreases steadily at the rate of 10 to the power minus 2 meter per second. A constant and uniform magnetic field of induction is there, that's 10 to the power minus 3 Weber per meter square, x perpendicular to the plane of the coil. What will be the radius of the coil when the induced EMF in the coil is 1 volt? We can write it's actually 1 volt is a very high induced EMF, right? We can write it equal to 1 microvolt, right? 1 microvolt, 1 microvolt, correct? So EMF will be nothing. It will be actually equal to T5 over dt. Talking about the magnitude only, right? That's T5 over dt. And phi is the flux. That's nothing. This is P a cos of theta, right? P a cos of theta. It's given that magnetic field induction acts perpendicular to the plane of the coil, right? If it's perpendicular to the plane of coil, perpendicular to the plane of coil, or we can say it's parallel to the area vector. It's parallel to the area vector of this coil, right? Or we can say the theta here is actually 0 degree. Theta here is actually 0 degree. If theta is 0 degree, B equals 0 is 1. So it will be E will be actually equal to d over dt of this PA, right? D over dt of this PA, right? Or we can write it as B is a constant here. That's dA over dt. That's dA over dt. Now the question is the radius of a coil decrease, right, steadily at the rate of 10 to the power minus 2 meter per second. And the radius of this coil is nothing. Its area of this coil is nothing. It's pi r square, right? Pi r square. We can write EMF as B times T over dt of T over dt of d over dt of pi r square, right? D over dt of pi r square. So it will be times pi. D by dt of r square will be twice r dr over dt, right? Twice r dr over dt. Now we have to find the what will be the radius of the coil when the induced EMF in the coil is 1 micrometer, right? So 1 microvolt, right? 1 microvolt means 10 to the power minus 6 volt is the induced EMF, right? This is the induced EMF. And magnetic field has the value here 10 to the power minus 3. Magnetic field has 10 to the power minus 3, right? Value. And pi 2 times r we have to calculate, and dr over dt is the rate of change of this radius, which is given as 10 to the power minus 2, right? 10 to the power minus 2, that will be equal to 10 to the power minus 6, right? So from here we can actually calculate the value of r. So 2r will be actually equal to 10 to the power minus 1 upon pi, right? Or we can say that our radius will be equal to 1 upon 25, right? 1 upon 25. So this will be the radius at which the induced EMF will be 1 microvolt, right? 1 microvolt, right? 1 microvolt. Now let's try to discuss this question as well. It's a very small question. A 10 ohm resistance coil has 10 ohm resistance coil has 1000 turns, right? It has 1000 turns. It means the value of N here is 1000, right? So 1000 turns are there in a coil, and the resistance of this coil is given as 10 ohm, right? 10 ohm is the resistance. It's placed in magnetic field of induction of uh, 5 into 10 to the power minus 4 Tesla, right? 5 into 10 to the power minus 4 Tesla, right? For a time of for 0.1 second, for 0.1 second. If the area of this cross section is 1 meter per square, 1 meter square, right? Area of this cross section is 1 meter square. We have to calculate the induced EMF, right? We have to calculate the induced EMF. The induced EMF will be nothing. It will be the d5 over dt, right? d5 over dt. d5 over dt, right? A 10 ohm resistant coil has, but it's a uniform magnetic field, right? If the area of cross section, you calculate the induced EMF, but there should be something. Magnetic flux should change through this coil, right? It's placed in a magnetic field of induction 5 into 10 to the minus 4 Tesla for 0.1 second, right? For 0.1 second, it means the value of this delta t, that's delta t is actually equal to 0.1, right? 0.1 second, right? So it will be d5. Phi will be actually, that's delta phi. We can talk about the average induced EMF. That's delta phi or delta t, right? Delta phi or delta t. At time t equal to 0, the magnetic field was 0, right? If the magnetic field was 0 at time t equal to 0, then the initial flux through the loop was actually 0. Then in 0.1 second, there is some flux, or we can say there is some change in flux through this coil, and there will be some slight or short induced EMF for a very short span of time, right? That we have to calculate. That will be del phi over del t. So del phi will be actually BA cos of theta, right? BA cos of theta and BA cos of theta, right? That will be equal to BA cos of theta, right? So there are 1,000 turns. We'll multiply it with 1,000 here, right? 1,000 turns. And the magnetic field is given, and the radius cross section is given 1, right? And it's given as 0.1, right? 0.1 second. That's a delta t. Magnetic field is 5 into 10 to the power minus 4 into A, that's given as 1 meter square, and there are 1,000 turns in it, right? Upon 0.1, right? Or we can say this induced EMF will be actually, uh, it will be actually 5 into 10 to the power minus 1 upon, right? Upon 1 into 10, right? Or we can say it will be a 5-fold, right? It will be a 5-fold of EMF induced in this coil, right? So 5-volt will be the induced EMF in this coil, right? Because of this sudden change in flux through the coil, right? Because of this sudden change in flux through this coil, right? So we'll stop here. In the next lecture, we'll be discussing about the self-induction and the mutual induction as well. We'll meet on Monday. Till then, take care and goodbye.